What is a thermal relays and how does it function? Thermal relays are electrical protection devices designed to prevent overheating of electric motors or other equipment by monitoring their temperature. They work by detecting the heat generated by excessive current flowing through the circuit. When the temperature exceeds a predetermined threshold, the relay trips and interrupts the electrical current, thus preventing damage to the equipment. Thermal relays are commonly used in conjunction with contactors in motor control circuits. They offer a reliable and cost-effective means of protecting motors from damage caused by overloads or faults. These relays are crucial in industrial applications where motors operate under varying load conditions, as they help ensure the safe and efficient operation of equipment. There are different types of thermal relays available, including bimetallic and electronic variants. Bimetallic thermal relays use the principle of differential thermal expansion of two metals bonded together, while electronic thermal relays rely on temperature sensors and electronic circuitry to detect overloads. Overall, thermal relays play a critical role in safeguarding electrical equipment from overheating and subsequent damage, contributing to the safety and reliability of industrial processes. Thermal relays come in various types, each designed for specific applications and operating conditions. Here are some common types. Bimetallic thermal relays are a type of protective device commonly used in electrical circuits to prevent overheating of motors and other equipment due to excessive current. Here's how they work and some key features. Principle of operation. Bimetallic thermal relays operate based on the principle of differential thermal expansion. They consist of two strips of different metals bonded together. When current flows through the relay, the strip heats up. However, because the two metals have different coefficients of thermal expansion, one metal expands more than the other, causing the strip to bend or warp. Trip mechanism. The bending or warping of the bimetallic strip triggers the trip mechanism of the relay. This mechanism is typically connected to a switch or contact arrangement. When the strip bends past a certain point due to excessive heating, it actuates the switch, opening the circuit and disconnecting the load. Adjustability. Many bimetallic relays allow for adjustment of the trip current or temperature setting. This adjustment is usually done by means of a screw or dial located on the relay housing. It allows users to set the relay to trip at a specific current level corresponding to the desired overload protection. Reset. Once the relay trips and interrupts the circuit, it typically remains in the tripped state until manually reset. This ensures that the equipment remains protected until the cause of the overload is addressed. Some bimetallic relays may include an automatic reset feature that allows them to reset automatically after the temperature decreases to a safe level. Applications. Bimetallic thermal relays are commonly used in motor control circuits to protect electric motors from overload conditions. They are often integrated into motor starters or contactors, providing an additional layer of protection for the motor. Advantages. Bimetallic relays are simple in design, reliable, and cost-effective. They provide effective protection against overloads and can withstand harsh operating conditions. Additionally, they do not require an external power source for operation, as they derive their energy from the current flowing through the circuit. Limitations. One limitation of bimetallic relays is their relatively slower response time compared to electronic thermal relays. They may also have limited accuracy and repeatability, especially in applications requiring precise trip characteristics. Additionally, they may not be suitable for very high current or high-frequency applications. Electronic thermal relays are advanced protective devices used in electrical circuits to prevent damage to equipment from overheating. Here's an overview of how they work and their key features. Operating principle. Electronic thermal relays utilize electronic components, such as temperature sensors, thermistors or thermocouples, and control circuitry, to monitor the temperature of the system. When the temperature exceeds a predetermined threshold, the control circuit triggers the relay to open the circuit and disconnect the load. Temperature sensing. Electronic thermal relays rely on temperature sensors to accurately measure the temperature of the equipment or system they are protecting. Thermistors are commonly used as temperature sensors due to their sensitivity to temperature changes. Thermocouples, which generate a voltage proportional to the temperature difference between two junctions, are another option for temperature sensing in electronic relays. Control circuitry. The control circuitry in electronic thermal relays processes the temperature signals from the sensors and compares them to the preset threshold value. When the temperature exceeds this threshold, The control circuit triggers the relay to trip and interrupt the circuit. Adjustability. Many electronic thermal relays offer adjustable settings for the trip temperature or current level. This allows users to customize the protection parameters according to the specific requirements of the equipment or application. Fast response time. Electronic thermal relays typically have faster response times compared to bimetallic relays. This enables them to provide more precise and rapid protection against overheating conditions, minimizing the risk of equipment damage. Digital display and communication. Some electronic thermal relays feature digital displays that provide real-time temperature readings and status information. They may also offer communication capabilities, allowing integration with control systems for remote monitoring and diagnostics. Integrated protection features. Electronic thermal relays may incorporate additional protective features such as phase loss protection, short circuit protection, and ground fault protection to enhance the overall reliability and safety of the electrical system. Wide operating range. Electronic thermal relays are suitable for a wide range of applications and operating conditions. They can provide reliable protection for motors, transformers, generators, and other electrical equipment in various industrial and commercial settings. Overall, electronic thermal relays offer advanced temperature monitoring and protection capabilities, making them ideal for critical applications where precise and fast-acting protection is required. PTC, positive temperature coefficient, thermistors are passive electronic components widely used for temperature sensing and protection in various electrical and electronic systems. Here's a detailed look at temperature sensing PTC thermistors. Operating principle. PTC thermistors are made of semiconductor materials whose resistance increases with temperature. Unlike NTC, negative temperature coefficient, thermistors, where resistance decreases with temperature, PTC thermistors exhibit a positive temperature coefficient of resistance. This means that as the temperature rises, their resistance increases. Temperature sensing. PTC thermistors are primarily used as temperature sensors due to their predictable and repeatable change in resistance with temperature. By measuring the resistance of the thermistor, it's possible to determine the temperature of the environment it's sensing. This property makes PTC thermistors suitable for applications such as temperature monitoring, control, and protection. Protective applications. In protective applications, PTC thermistors are often employed as self-regulating heating elements or as components in overcurrent and over-temperature protection circuits. When used in these applications, the thermistor's resistance increases significantly when the temperature exceeds a certain threshold, thereby limiting the current flow and providing protection against overheating. Inrush current limiters. PTC thermistors are commonly used as inrush current limiters in power supply circuits and electronic equipment. During power-up, when the electrical device is initially switched on, there is often a surge of current due to the charging of capacitors and other components. PTC thermistors help mitigate this surge by initially presenting a low resistance, which limits the inrush current, and then transitioning to a high-resistance state once the circuit reaches a steady-state condition. Thermal time constants. PTC thermistors have characteristic thermal time constants, which define the rate at which they respond to changes in temperature. This property is important in applications where rapid temperature sensing and response are required. Advantages. PTC thermistors offer several advantages, including high sensitivity to temperature changes, reliability, low cost, and compact size. They are also easy to integrate into electronic circuits and require minimal power to operate. Varieties. PTC thermistors come in various shapes, sizes, and temperature ratings to suit different application requirements. They can be encapsulated in epoxy, ceramic, or other materials to provide mechanical protection and environmental robustness. Limitations. One limitation of PTC thermistors is their nonlinear resistance temperature characteristic, which may require compensation or calibration in some applications. Additionally, their response time may not be as fast as other temperature sensors such as thermocouples in certain high-speed applications. Overall, PTC thermistors are versatile temperature sensing devices with widespread use in temperature measurement, control, and protection applications across numerous industries. Bimetal strip overload relays are protective devices commonly used in conjunction with motor starters or contactors to safeguard electric motors from damage due to overloads. Here's an overview of how they work and their key features. Principle of operation. Bimetal strip overload relays operate based on the principle of differential thermal expansion. They consist of two metal strips bonded together, each with a different coefficient of thermal expansion. When current flows through the relay, it heats up the bimetal strip. The strip with the higher coefficient of thermal expansion expands more, causing the bimetal strip to bend or warp. Trip mechanism. The bending or warping of the bimetal strip triggers the trip mechanism of the relay. This mechanism is typically connected to a switch or contact arrangement. When the strip bends past a certain point due to excessive heating from an overload, it actuates the switch, opening the circuit and disconnecting the motor from the power source. Integration with motor starters. Bimetal strip overload relays are often integrated into motor starters or contactors, forming part of a motor control circuit. They are typically mounted adjacent to the contactor and connected in series with the motor supply lines. Adjustability. Many bimetal strip overload relays offer adjustable settings for the trip current or temperature. This allows users to customize the protection parameters according to the specific requirements of the motor and application. Reset. Once the overload condition is cleared and the motor cools down, the bimetal strip returns to its original shape, resetting the relay. Some relays may include a manual reset button or lever, while others may reset automatically once the temperature drops below the trip threshold. Accuracy. Bimetal strip overload relays provide reliable and accurate protection against overloads. However, their response time may be slower compared to electronic overload relays, particularly for small overloads. Advantages. Bimetal strip overload relays are simple in design, robust, and cost-effective. They do not require an external power source for operation and are suitable for use in various industrial applications. Limitations. One limitation of bimetal strip overload relays is their relatively slower response time compared to electronic overload relays. They may also have limited adjustability and sensitivity compared to electronic relays, making them less suitable for applications requiring precise trip characteristics. Overall, bimetal strip overload relays are widely used for motor overload protection in industrial and commercial settings, offering reliable and economical protection against motor damage due to overloads. Thermocouple-based relays are protective devices that utilize thermocouples for temperature sensing and relay control. Here's an overview of how they work and their key features. Principle of operation. Thermocouples are temperature sensors made of two dissimilar metal wires joined together at one end. When the temperature at the junction, measuring point, changes, it generates a small voltage signal proportional to the temperature difference between the measuring point and the reference point, usually at ambient temperature. This voltage signal is utilized by the relay for temperature monitoring and control. Temperature sensing. Thermocouple-based relays use the voltage generated by the thermocouple to measure the temperature of the system or equipment they are protecting. As the temperature changes, the voltage signal from the thermocouple varies accordingly, providing a continuous indication of the temperature. Relay control. The voltage signal from the thermocouple is processed by the relay's control circuitry. When the temperature exceeds a predetermined threshold, set by the user or the relay's design, the control circuit triggers the relay to open or close a contact, thereby controlling the operation of the protected equipment or activating an alarm. Types of thermocouples. Thermocouple-based relays can be configured with different types of thermocouples depending on the temperature range and application requirements. Common thermocouple types include Type K, chromoaluminal, Type J, iron constantan, Type T, copper constantan, and Type E, chromal constantan, among others. Accuracy and calibration. The accuracy of thermocouple-based relays depends on the accuracy of the thermocouple itself and the precision of the relay's control circuitry. Calibration may be necessary to ensure accurate temperature measurement and control, especially in critical applications. Response time. Thermocouple-based relays typically offer fast response times, allowing them to quickly detect temperature changes and respond accordingly. This rapid response is beneficial for applications where precise temperature control or protection is required. Applications. Thermocouple-based relays find wide application in industries such as manufacturing, HVAC, heating, ventilation, and air conditioning, automotive, and process control. They are used for temperature monitoring, control, and protection in various equipment and systems, including ovens, furnaces, boilers, refrigeration units, and industrial machinery. Advantages. Thermocouple-based relays offer several advantages, including high accuracy, wide temperature range, ruggedness, and compatibility with harsh environments. They are also relatively simple to install and operate, making them suitable for a wide range of applications. Limitations. One limitation of thermocouple-based relays is that they require careful installation and proper wiring to ensure accurate temperature measurement and reliable operation. Additionally, they may be susceptible to electromagnetic interference, EMI, and noise, which can affect their performance in some environments. Overall, thermocouple-based relays provide reliable temperature monitoring and control solutions for various industrial and commercial applications, helping to ensure the safe and efficient operation of equipment and systems. Self-heated thermal relays are protective devices used in electrical circuits to detect and prevent overcurrent conditions, particularly in motor control circuits. Here's an overview of how they work and their key features. Principle of operation. Self-heated thermal relays incorporate a heating element that is energized by the current flowing through the protected circuit. The heating element generates heat proportional to the square of the current passing through it. According to Joule's law, P equals I squared asterisk R. As the current increases due to an overload condition, the heating element generates more heat. Temperature sensing. The self-heated thermal relay monitors the temperature of the heating element using a built-in temperature sensor or a bimetallic strip. As the temperature of the heating element rises, it indicates an increase in current flow beyond the normal operating range. Trip mechanism. When the temperature of the heating element reaches a predetermined threshold, indicating an overload condition, the trip mechanism of the relay is triggered. This mechanism may involve a bimetallic strip that bends or warps due to the increased temperature, activating a switch to disconnect the circuit. Adjustability. Many self-heated thermal relays allow for adjustment of the trip current or temperature setting. This adjustment is typically done using a dial or screw on the relay housing, allowing users to set the relay to trip at a specific current level corresponding to the desired overload protection. Reset. Once the overload condition is cleared and the heating element cools down, the relay resets automatically. Some relays may include a manual reset button or lever for resetting the relay after a trip. Integration with motor starters. Self-heated thermal relays are commonly integrated into motor starters or contactors as part of a motor control circuit. They provide an additional layer of protection against overcurrent conditions, complementing the primary motor overload protection. Advantages. Self-heated thermal relays offer reliable and effective protection against overcurrent conditions, particularly in applications where motors are subjected to varying load conditions. They are relatively simple in design, robust, and cost-effective. Limitations. One limitation of self-heated thermal relays is their slower response time compared to electronic overload relays. They may also have limited adjustability and sensitivity, making them less suitable for applications requiring precise trip characteristics. Overall, self-heated thermal relays provide essential protection for motors and other electrical equipment, helping to prevent damage from overcurrent conditions and ensure the safe and reliable operation of industrial processes. These are just a few examples of thermal relays, and there are variations and combinations based on specific application requirements. Each type offers advantages and limitations depending on factors such as accuracy, response time, sensitivity, and environmental conditions.